So our next talk is Searching for Dark Matter with XENON and Pegasus by Evan Shockley from UC San Diego. Welcome, Evan.
Thank you. Can you guys see the screen okay? I never know because I have multiple.
Yeah. Yes, we can. We see
Okay.
you and the screen both. So
Okay, great.
Thanks.
All right, well, hi everyone. Thanks a lot for organizing this and inviting me. So I'm a postdoc at UC San Diego, working on the XENON collaboration. I'll tell you about how we use Pegasus to search for dark matter with XENON. All right, so first I want to start with dark matter. So we have a huge amount of evidence from astronomical and cosmological observations that there exists this stuff we call dark matter. We know it doesn't interact with light, but we know it exists from its gravitational effects. So one piece of evidence that's often pointed to is called the bullet cluster, which is shown here, which visualizes nicely what this dark matter is. So this is a cluster of galaxies that have just collided with each other. And the mass of this system was measured in two different ways. So like the matter content of this distribution was first measured by just pointing at telescopes at it and basically seeing how much light is coming out of it, which gives you the mass distribution shown in red. And then you can also measure the mass using gravitational lensing, which just tells you how much gravity essentially is in the system, which when you do that, you get the result shown in this purplish color. So you can see that there's these two very distinct populations, which is one of the strongest pieces of evidence where I always point to the title of this paper is a direct empirical proof of the existence of dark matter. This is a very strong piece of evidence that there's this stuff that doesn't interact with light, but interacts gravitationally and is a huge component of the universe. So this is one of the biggest open questions in physics today, because all of the different pieces of evidence, this is just one of them, but all of them point to dark matter vastly outnumbering all of normal matter. So every planet, star, galaxy cluster, et cetera, by about 5 to 1. And so this is a huge component of the universe that we don't know what it is, and we'd like to understand it more. It's a very fundamental question. So based on the observations we think that it could be a new fundamental particle that we just haven't detected before. Based on those observations, we know that it has to have some property. So it has to have mass because we see its gravitational interactions. It has to interact with normal matter very, very rarely, if at all. And it has to be stable relative to the age of the universe because we know that it's been around for a long time. And there are some theoretical predictions for what type of particle this might be. So things like WIMPs or axions, and there are many others I won't go into here. And so there's a lot of experiments to go search for these particles, which is what XENON does. So we're trying to detect these particles directly, which one thing that I think is pretty cool is that to try to search for this dark matter that's out in space at cosmological scales, we go deep underground. So the XENON experiment is in the Gran Sasso National Laboratory in central Italy. Here's a picture of the lab. This is the office building that's above ground. And then under this mountain, there's the underground lab that has a number of underground experiments, with XENON being one of them. Here's a picture of the detector. The heart of the detector is the time projection chamber, or TPC, that's filled with liquid XENON. At the very center here, this is what we're searching for dark matter interactions in. So since dark matter is expected to interact so rarely, it will just pass right through the mountain and hopefully very rarely interact with the XENON atoms in this very, very sensitive detector. That's the basic idea. This detector sits in this 30-foot tall water tank that's filled with ultra pure water to act as further shielding of the detector. And then this is a 3-story building that houses just infrastructure. It's like XENON purification, data acquisition, XENON gas storage, and some calibration equipment. So the XENON project has been going on for some time now with multiple phases. So it started in the mid-2000s with XENON-10, which was about 15 kilograms of XENON, the kind of a prototype just to show the first detection principles of this type of experiment. This was upgraded then to about a 100 kilogram detector called XENON-100, which was a leader in the field for some time, about 10 years ago. Then in kind of the mid 2010s, XENON 1 ton came along, which was the first ton scale xenon experiment of this type, which just finished taking data about 2 years ago. Has a total mass of 3 tons and is the most sensitive dark matter experiment to date for most of the dark matter candidates that exist. And yeah, currently still has the most stringent results. We very quickly upgraded XENON 1 ton to XENON ton, where N here is about, depending what mass you use, about 7 or 8 tons. And this is currently being commissioned. It's already been, you can see here that the TPC has been assembled. It's been installed underground, and we're currently commissioning it as we speak. So it's a very exciting time. Where this is, will run for about 5 years. This is kind of what we expect to be the flagship kind of experiment of the XENON program. We'll run for quite some time looking for dark matter with unprecedented sensitivity. I will just say in the future, there's a proposed experiment called Darwin, which is even huge, like, tens of tons of liquid xenon, which is, something like 10 years down the road, if funded and things like that. So how does the detector work? I always like to describe it as these TPCs are particle detectors that are able to reach very low background, meaning that the total number of events from just like everyday radiation and things like this is very, very low, especially at the center of the detector, which you need in order to search for these rare interactions from dark matter. You need a very low energy threshold because the dark matter we know is not moving very fast relative to the Earth. So the scatters that occur are very low energy. So you need a keV scale energy threshold. And then again, because the events that we're looking for are so rare, you need to have you want to have as large a detector as possible to increase the probability of seeing something. And you want that detector to take data for as long as time as possible. So as I just showed, the XENON experiments are kind of excel in both of these. So we're able to reach ton scale relatively quickly, which helps with our sensitivity a lot. So how does the detector work? So a particle such as dark matter, but also just like everyday radiation, I should start. So the detector is made of both liquid and gaseous xenon. It's called a two-phase xenon time projection chamber, where the most of it is this liquid xenon bulk here. This is where the interactions occur. And then there's this thin gaseous layer at the top. So the way it works is when a particle comes in and scatters in the liquid, it'll produce both scintillation light and ionization charge, so photons and electrons. Those photons are immediately detected by photodetectors that line both the bottom and the top of the detector. These are just photomultiplier tubes. Over that first photon signal is called the S1, immediately detected after the interaction. So then while that's going on, these electrons that were produced at that same interaction are drifted to the top of the detector using an electric field. They're then extracted into the gas. This produces another flash of light that is then detected by those same photodetectors. We call that second signal S2. And so what you get is just a waveform on every PMT that has some S1-like signal followed by order of millisecond later, this S2 signal. And based on these two signals, we infer a lot about the type of event that occurred. So things like the energy, the position of the event in 3 dimensions, and then also a form of particle identification, which I won't go into, but I'll just say it's really important for discriminating dark matter-like signal events from everyday background events, which is a very powerful feature of this detector. So that's kind of the schematic. What this data looks like in real life is shown here. This is just an example waveform from XENON 1 ton that I had laying around. So here it's just the start down here. So it's just on the x-axis is just time. So the total event window is about 2 milliseconds. And then in that event window, we're looking for any PMT to trigger even on a single photon level. So that the trigger is set to have a single PMT triggering on a single photon at least 90% of the time. So we're triggering on about as low as you could go, which is over the full 2 milliseconds. So then on the y-axis here is the PMT channel number, where then each red dot is a a hit, we call. So basically something that could be one or more photons. And then our reconstruction looks in this waveform over all the PMTs to look for these S1 and S2 signals. So here you can see the sum waveform, which is just adding up all of the PMTs, where it found an S1 signal right around here with a zoom in, of the S1 shown in the top left. And it found an S2-like signal here with a zoom shown here. And then you can also see which PMTs saw which amount of light. And then that also includes the position reconstruction with this red X to give you an idea. So this is what the data looks like. And then I just want to mention that it's kind of non-intuitive, at least to me. It's that while this is a rare event search, we're trying to push the number of events down as low as possible. Because we're triggering on such low signals and we have such a big detector and so many PMTs, the data size can actually get relatively large. So XENON 1 ton was order of a petabyte per year. And XENON ton is probably, I think we'll have at least a factor of 2 or 3 more than that, maybe as much as a factor of 5. So we're at multiple petabytes per year, which that data needs to be processed. So for XENON ton, we have a brand new data processor. It's called STRAX. It stands for Streaming Analysis in XENON. It's written completely open source, written by current and former members of the XENON collaboration. And the idea is that the detector is basically just streaming out data in time. So everything is kind of referenced to the time of different interactions, and there's there's no like event level trigger at the DAQ. Everything it's just like a streaming coming out of the detector, which is really nice for analysis, but actually complicates the data structure quite a bit. It's written in pure Python, but we use just-in-time compilers like Numba to increase performance to be at the level similar to what you'd have at a C or C++. One consequence of this is that in order to get that boosted performance, we need to simplify the data structure significantly. So in particle physics, we often want to have like complex object-oriented data structures with different classes inside of classes, things like this. This doesn't work well with just-in-time compilers. So what you want is just a tabular data structure. So to get around this, we have many different tabular data structures. So that's what this graph over here is showing. Each node is a data type, basically a directory that has tabular like data inside of it. And then each edge of this is some algorithm that produces that data, where then the different data types have different dependencies on other data types. So at the lowest level, we have raw records. This is the data that's coming out of the DAQ. It's about 100 gigabytes per hour with very wide variation on this. So calibration data could be 10 times more than this. But so this is quite heavy. And then at the very top, it's like itty bitty, 10 megabytes per hour, something like this, where then there's huge amount of processing in between those two. One thing that is cool of this type of data format is that each of these data types have their own kind of versions and configurations. And we handle their version control using a hashing system, which I think it's easiest just to show an example. So this is a single run. It's labeled run 12,000, so an hour of data. The data type was event basics, but you can see there's 4 different hashes where these correspond to either different version or configuration in the algorithm that creates this data type, or in the configuration of any of the data types it depends on, so anything below it in this graph. So this is kind of how we handle the version control of this, which, as you can imagine, this complicates the data management significantly, but it's really nice from an analysis standpoint. Luckily, since this high-level data is so light, we can keep all of this, essentially all of this on a single site. So we have our main analysis site is the Midway cluster at University of Chicago. And we can, for all of our data, we've taken at least most of it, we can keep all of the high-level stuff just on the allocation we have there. We cannot do that with the low-level data, however. So this is far too heavy. So this is distributed on grid storage across both US and Europe. And it's managed by the Rucio data management system. So here's, doesn't show all the sites, but here's We have the main site in the US is an endpoint in Chicago, and then we have several sites in Europe where we host our raw data, where we can then easily download using Rucio, and Rucio maintains data integrity and things like this. But if we want to process this data, since it's distributed, we want a distributed data processing framework as well. And so we have the software we use for this, we call it Outsource, which is essentially just a wrapper around Pegasus, where we just inject in the XENON specific run information and stuff like this to create the workflows. Where the idea is pretty simple. We want to process these single chunks of data all in parallel. These are all single core jobs where we have about 1,000 chunks per hour of data, and we'll process something like 10 or 20 chunks per job. So it's pretty straightforward. The one cool thing is that since our data is heavy compared to the time it takes to process it, we're very much storage limited. So what we do is, thanks to a lot of help from Mats, is we submit our jobs to where the data is. So we can submit from the submit host in Chicago directly to the European grid, which includes sites at many of these where the data is. So we can even submit directly to Nikev cluster where we have an allocation which hosts a lot of our data. So then we don't have to be moving data back and forth across the Atlantic, which is really nice. So this here just gives you an idea of what the data looks like. This is the raw records of some small run, just broken up into little chunks where each chunk is just the waveforms of like 3 seconds of data, something like this. And yeah, for this part, we're focusing only on the low level data because this is the one that's heavy. So just to walk you through an example, let's say that we had an update to the algorithm that creates peaklets. This is kind of the first data that you start to merge those hits together to things that might be S1s or S2s. To reprocess this, you need to first check if the records that data type requires is available somewhere on the grid. So maybe there's an update that also changed records, in which case you'd have to recreate that. If records does exist, we just create a one-layer kind of diamond-like DAG and submit that, and it's a relatively simple workflow. If the specific records does not exist, we have to go back another layer and reprocess records from raw records. So this just adds another layer, very similar processing. Everything's essentially the same. You just swap raw records and records. On the job, this is what it looks like. So you just will download the chunks that you want to process using Rucio. We process those with that Strax reconstruction software to look for whatever the algorithms we need to run on it. The outputs from each job then get staged on our Dcache system in Chicago, to wait to be merged for all of the processing jobs to finish. Once that happens, they all get merged together and uploaded back into Rucio on whatever grid site we want to put them on. And then if we need to keep continuing up the graph, we do that if necessary. So here's an example of how this looks like with an example run that I submitted. This is one that we needed to do both layers. So it's just, it's like a diamond-like DAG. First, you have the raw records to records processing with these Strax wrapper jobs, where then they get merged with this combined wrapper, uploaded into Rucio. So then the records data is now available. Once that finishes, it spawns off those peaklet processing jobs, shown at the second layer, and then it will finish with the merging of those jobs. So relatively straightforward. I will say, so right now, we're only focused on the low-level data because that's the data we really need OSG for. In the future, we do want to keep moving up that complicated graph that I showed you, which is easy to do in Pegasus, which is really nice. But right now, we just don't need to do it, so we haven't yet. But that's in the pipeline in the next couple of weeks. Hopefully, we can get that working. I will just say, I've mostly been focusing on the data processing. We also do Monte Carlo data production with Pegasus. We've actually been doing this longer than the data processing. This goes back several years now. Where instead of taking data from the detector itself, we create fake data using XENONt4, we then pass that fake data into a waveform simulator that turns it into the exact same format that a real data from the detector would look like, which from there it can go through the exact same processing chain like the normal detector data. So this is also very much under development right now. At the moment, it's relatively simple. You just would submit something, like in this case, it was 20 jobs. Each of those jobs simulates, I don't know, 1,000 events. Those 1,000 events get passed to a waveform simulator and then get processed all on the same job, where then the output gets merged together. Very, very simple. But we're working right now on a more complicated, more layered workflow, which I think will help things a lot, where you can break apart the different tasks. Sorry, I'm going over time. To summarize, yeah, nature of dark matter is one of the biggest open questions, and XENON is on the forefront of this search. And Pegasus is a critical component of our experiment for sure, critical to getting the analysis, the final analyses out. I want to thank especially Mats Ringe for all the support. I pester him, I think, almost every day about various things. So huge thank you to him and the whole Pegasus team for everything you guys have done. So thanks a lot. For Pegasus feedback, I'm still relatively new. I don't feel quite qualified to give good feedback. I will just say a few things. There are some things I love that I'm a naive physics postdoc, but things that I didn't know could work so easily in the past that do. So I think the monitoring statistics is really nice compared to what I'd used in the past. I really like the way that the transfers are handled, how you don't really have to think about it after you start the workflow. Everything gets staged for you on the various sites. And another thing that is the graph viz. It's really fun making that for these slides. One small request, I don't know if this is already available, but for the graph viz, it'd be nice if you could go directly to PNG or PDF. Right now it just goes to DOT, I think, which is easy to convert, but it might be nice just to be able to go straight to an image. And then I think this is kind of echoing some of the other stuff people have said, but during development, if something fails, sometimes I'll also say sometimes it's hard to find the exact error, like others have said. But the thing that I've had an issue with, which I don't know if it's just my naivety, but if something fails, I often want to just modify the executable quick, change some line or add a debug statement or something, and then resubmit the rescue DAG. But I ran into an error where this changes the checksum of that file, and then the resubmission fails using Pegasus run. I don't know if there's a way around this. I usually just resubmit the whole workflow, which isn't the most efficient. But that was one thing I thought of while making these slides. And yeah, thank you all. Sorry, I went a couple minutes over. Thanks a lot for organizing this.
Thank you so much for your talk, Evan. It's really great, and I appreciate your feedback. I think Karen has an answer to the.
Yeah, I think Rajiv already covered it in Slack, but like it was an interesting checksum use case that we've never really thought of how it can affect a person adversely. But in general, with 5.0, we also introduced a notion of a Pegasus mode, where you can just say, Pegasus mode is tutorial development or production, and then we automatically turn off checksums for you. So let's say you're in a development style mode, then that might be one way to go about it. So,
yeah, I think that'd be perfect.
Yeah. So we'll point you to the documentation.
Cool. Thanks a lot.
And now that's why we're having this meeting, is exactly to hear your feedback and think about things that hear about things that we didn't think about. So this is super valuable for us.